halfway through the course and we'll be starting it soon. It will be ending soon. So I'll start by introducing myself. It's like we don't do it usually, but yeah, yes. So I'm Jagriti. I'm doing PhD at IIT Gandhinagar with Professor Kalamarkadu Shekhar at the Muse Lab. I'm working on ultrasound imaging. That's on quantitative ultrasound imaging to differentiate between two different types of tissues based on its microstructure. So that's basically tissue characterization in order to it's like quantify whether there is like this particular tissue or a structure has more number of more concentration of cells or not, or if there are scatters of or cells who have higher sizes or lesser sizes. So I do model different parameters. I see if the envelope statistics, how it varies, and how which particular significant parameters are we able to extract from the envelope statistics. So because of that, I chose this course, biomedical signal processing, today because it aligned well with my interest, and I'm also doing a similar kind of research over here at IIT Gandhinagar. So today's what we'll be going through is week number 10, where we saw that there are a number of tutorials which are given. So as we discussed previously, that what we'll essentially do is, first we'll just see the theory behind it, and then we'll go towards the numerical part. So in towards the numerical or the coding part. So today's lecture will be seeing the coding part of it, and then accordingly, if you're not able to understand or anything as such, then we can always go behind the previous lectures. All the lectures are recorded, and you can also view them on YouTube, so you can also have a look there. So that's it from my side, and we'll start for today's session, live session. Just give me 2 seconds. I'll share the screen from my second device. Yes, perfect. Okay. So we'll be going through week 10, but what I essentially saw that week 10 is a total of tutorial that are solved. So we'll directly go to one example as such, and then we'll do the tutorial assignment tab. Okay. So here we saw that sir has given us a couple of like there are different tutorials for now. For now, I have only saved the tutorial one. Then we also have tutorial 2 and then tutorial 3 followed by it. So what we see is, sorry. Okay, so we have .m file. So what .m file is nothing but a script file of MATLAB. So whenever you make a file and then you save it to the extension in which that particular file is saved, that is .m. So that is nothing but how a MATLAB script is being saved. Next is nothing but these are all the data files. So you can also always double click the data file and then it's like import the data from that own data file. So here you're not able to say okay it's loading, but then you'll okay. So here are all the data numbers or files that you have, and it's all a row vector. So again, for your information, that MATLAB, so it's nothing but restricted towards 2 cross 60. So we have these two numbers, but in MATLAB, so upper one might be a header for the same, but in MATLAB there's always a restriction for row vectors. So it's always it's like told that beforehand that you can always make numerous of vectors, or it might go towards infinity in the column vector but not in the row vector. So you can always stack your data in column vector. Okay. uh, 2 minutes. I'll see what's going on back there, and I'll join again. Okay, so then these are all the editor as auto saved files. So normally what we see that a file which is just going on and you're working on a file and that's not, it's like it is saved completely, but there's some progress going on in that particular file. So then MATLAB makes an editor auto save for the same. So this is how the structure of MATLAB is, and then you can always change the format that you want. You can always have your workspace variables stacked over here. This is the command window where you can do anything directly without adding a semicolon to it. This is the workspace window where you'll have all the variables stacked up and then the values or array size associated with it. Then you can also in this mostly it's not stacked like this, but in mine I have said that okay, group by the number of functions that I have or type that they are. So it will always help me characterize or differentiate all the script files from the functional files. So it will also have a separate header for the function files. So I'll show you it's like one such example. I have one project. I don't know if it has some function. Okay, so here, so I have one function file over here, and then I have a script file. So script file is .m, whereas a function file is also .m. But then in this particular kind of file, it's like you might have made functions in C++ or say other coding languages, where you see that how you make a function is nothing but an output argument, then your name of the function. So this name of your function is essentially the same as that of your file name times the input parameters that you have inside. Sin next. Sorry for the noise. Someone's doing out there. So okay. So we'll go back on our tutorial one. So I saw and then I've just clubbed everything so that you just know how things are supposed to be done, and then you can always go back behind and then see how the code was or how it was manipulated. So for it's like till now I suppose that you all know that how do we make plot, how do you it's like load data and then do the magnitude space vector of the same, find the SNR. So we'll just go through the same prerequisites again. So here, once this data sample was given to us, say this elephant data, high frequency data, low frequency data, and then this is a random data that's being given. So in not normally what we do is like we'll load the data. Now if it's in MATLAB, we'll do load data because the mat file are normally will be loaded. But then if it's on Python, then you'll have to import another library where there in that particular say SciPy, and in that library you'll have a function called as loadmat or loadat. So you'll load it accordingly. Then you define the sampling frequency. If center frequency is given to us or the it's like resonant frequency is also given to you, then you find the sampling frequency from the Nyquist frequency criteria. Say take it as 2 times of maximum frequency or 4 times of maximum frequency. So here sampling was given. Okay, let it be. Then you have a data. Now the it's like what's essential to be done is like at first you always do say you okay, I have imported the data. I see the data is of size 9519 cross 1, so it's nothing but a row vector. Now since we stacked it, so it's a column vector. Then we see okay, the sampling frequency is this. Now you also had to know that what's the length of the vector. So essentially this is a just single dimension vector, so you know it would be 9519. But what if it was stacked into n number of cells? What if the transducer from which you were recording, it was not only a single element transducer, but it was also a linear array transducer. So one element had one line of data, second element had another line of data. So what if the data was stacked? So you always need to know what's the length of your data. Then from the time from the sampling frequency and the length, you can always estimate the time vector. So how do you find it? So okay, let's evaluate this then. Sorry. So from evaluating, we have the sampling frequency and the length in our workspace. Then we find the length time of the vector. So how do you find time is nothing but the entire length divided by the sampling frequency. Now initially our vector data was sampled in frequency domain. Now we need to convert it into time domain. So how do we do so? It's like nothing but converting the frequency to time. So 1 by f times the entire length of the frequency. So colon here denotes is like 1 to the entire, it's like 1 to end. And then you make a figure. So how do you make, it's like now there are two things. Now if you directly do a figure and then somewhere else you also write a figure, it will overwrite on itself. Then if you do something like this and write a number to it, then this figure will only figure number one will only have this data in it. So let's plot the time and ECG. So we see that okay, you have something like this. Now this is something that your baseline is not constant. It's like wandering baseline. It's been fluctuating very nicely. But here from here you can see that you have this P, you have this QRS, then you have this TUV. But there's this isoelectric segment. So what we saw that our this TUV segment was not that high in amplitude with respect to the P wave, but here it is. So there might be some abnormality going on, but now for now we aren't focusing on that. We are only focusing that how do you filter the data, how do you find the transfer function of the data. So for one such example, here we took a transfer function of h of z, that is 1 minus z raised to minus 1. So you don't have any poles over here, you only have zeros. So how do you write? So okay, if this is some another example where you took it like that. Now say if it's like this, you'll have minus 1 and this is only 1 0. So this is figure and find the transfer function of the same. So this nothing but PZ plot stands for polar zero plot. So you just pole zero plot. So give a transfer function, write its coefficient, and then make a plot. So this is how it makes this map. Now you can do some beautifying functions over here. So what else you can do is like make the axis bolder, add this as in a more bolder values, or increase their weights, it's like differentiating between the font styles. So the ones here you have your poles and then the zeros. So how do you find the it's like the frequency response of your vector, so or of your filter that you have designed. So first is nothing but the magnitude spectrum that we really do. So how, from where the magnitude spectrum is derived? It's derived from the frequency response. So take the frequency response. So what's the function for the same? So this is nothing but this will give you the impulse function, whereas this will give you the frequency associated with it. So you give the coefficients, the length of the vector, and the sampling frequency. So from there you can determine. So here we have used one such function called as subplot. I hope you all know that. Now given a figure, it makes the entire figure into a one plot. Now if you do subplot, it will differentiate your plots into n number of divisions that you really have. So or if you want. So here I have 2 times 1 times 1. So I have a it's like a subplot of, so this is same as m cross n. So m cross n. So rows cross column. So two rows cross one column. So I have two rows, one column, and the first would be my this one, and the second would be my this one, the phase spectrum one. If at all it was like it's like 1 comma 2, then it would be is that one row and then two columns. So it would vary. So it's nice in a way that you can see the different functions all together. So let's see how the magnitude spectra and the phase spectra looks like. So this is how the magnitude spectra looks like. But then the phase of the function is nothing but continuously declining at high frequency. This more of suggests us that okay, it will converge at some point, and then this saturates at some other point at the same frequency. So that's all you can derive from it. Next is nothing but now let's filter the data that we have. So given the transfer function inputs, let's filter it and see the input signal with respect to the output signal. So okay, here's how we got, this is our output signal and this is our input signal. So very noisy, differentiated, and we got something new. Yeah, yes. I don't know why it is flipped. We can get back on it, but what happened just now? This is your input signal, whereas this is your output signal. Then it's plotting reversely. We'll see. I'll see and let you know. Okay. So similarly, then you can always find the SNR of the filter. So how do you find the SNR of filter? You take some reference signal. In this case, I don't have a reference signal, but take a reference signal, find the noise as that reference signal minus the filtered signal, and then square of the energy, because since we are dealing with SNR is essentially the ratio of two energies of the signal and that of the noise. So you do take the square of the noise as well, and since everything here is discrete and defined in terms of time steps, so you sum them all up. You don't take an average of it, and then okay, wait, someone's waiting. Okay, So what normally what they have seen that for this kind of filter, say a notch filter, if you increase the pole radius, that is nothing but if you increase the number of poles that you have over here or the radius in between them, you see that the filter is nothing but a very ideal filter. Then there's a very sharper change over there. The notch also varies, but then this is a kind of thing that you can pay more attention to, is that at adjacent frequency the attenuation increases. This is the reason that why you saw that the phase response was that's okay. Something here when you saw that. Okay. So the same thing that happened to us, that it's overwriting in between the plots. So it's always better than safe. So just add numbers to your figures whenever you do so. So here we saw that okay, the phase response was decreasing with respect to frequency, so it's essentially attenuating at higher and higher frequencies. So as your again pole moves towards the zeros, the notch bandwidth will decrease and it will approach the ideal notch filter. So it will be a very sharper filter. Next such example from the other exercise was that you have again the function, the ECG data is given to you, then you define the length, the time, and then just try and see if your filter is then like what your signal is like. Now here we see that we have this nice strong it's like spikes in between your data. Now we are not really sure that if they are actual a physiological signal or it's something that's just as existing there due to noise. So then we saw that for this kind of signal the linear filter it fails to perform, because when the signal and noise spectra will overlap, so we really don't know that was like what is our signal as well as what is our noise, so we can't differentiate in between both of them. So synchronized averaging is useful over here, but then only when you are doing your noise is random with zero means you don't really see any fluctuations within noise. It's very constant, it's very periodic, and then it is uncorrelated with the signal, and the signal is stationary or quasi-periodic. So saying that signal might be stationary or it can be quasi-periodic, noise should be random and then periodic. So random and periodic not is like usually fall in the same lines, but then here for us to see that okay when the noise is random and then it's also with zero mean, it's just a hint that it should be periodic and then should be coming or continuously varying after a particular time. So what we do here is that one such thing here was about peak detection and take the template and then differentiate it. So they took a template of say around starting from this, and the length of template to be say 800 or 801. Then how do you take the template extracted? So you have your original signal in this. Now you index it out. So take it from this value to the ending value. So whenever you have a length of vector, say something, then when you enter the values for it, if it's from 0, it would be towards the end value. If it's from 1, if it's from 0, it would be end minus 1. If it's from 1, it would be end. So here if you start from a particular value, say a 0 value, then you end at something minus 1, like that. So let's run it. We run that, and then similarly you differentiate, take the time from it and try to see if your template is. So okay, this is how my template looks like where I'm trying to plot. Now here you essentially see that this is my QRS complex, this is TUV, and this is the isoelectric segment. That was not visible when we plotted just the signal itself. So do you see the isoelectric segment here? No, right? But here when you plot it, you actually I see a isoelectric segment over here. Okay. Yes, more plots are open. Okay. Then what you do is that next thing over here was to find a cross correlation or something. So how do you do is like, okay, you have a vector, say you padded it. Now if you remember how did we do cross correlation, convolution was taking a signal, flipping it, or add some advance and delay the signal, multiply both of them, and in the end add all of them. If it's a in discrete domain, add them. If it's in continuous domain, integrate them. So here it's everything in time step. We are doing everything in time domain. We are not yet going into frequency domain. So we'll essentially multiply and sum them, multiply and sum them. Okay. So you have your template, and then you have a signal that's padded up. That's from one to particular value, taking your ECG value inside. So multiply both of them, and when you do the cross correlation, take the sum of all divided. So normalize it. So how do you normalize it? You do the normalization of the template as well as normalization of the padded template that you have. Okay. So then you again plot it. So you saw that okay, this was your initial input signal, but then when you did the cross correlation, you see it has much more improved. But then over here, you're not able to differentiate actually what is where and how this went. So now you have get rid of this bigger artifacts and the energy is being normalized. Everything's nice looking, but then here you don't know what is being going on over here. So for the same, what they do is that synchronized averaging. So take a threshold, above this threshold keep everything, below the threshold discard everything. So now just to ensure that if you have a signal within that range, you with the if loop give a condition that if this exists and this exists, then only you'll take the signal and then it's like essentially average it out, and in the end you mean it. So when you do so, what you see is that you get actually a very smoothened signal. But this is just because you are plotting a very small template. Now if you do this for the entire window, it might not work. So for the same, what you need to do is that you need to, it's like sample a particular window, sample another window, next window, and then concatenate everything. You can't essentially take the entire data and then do it. So you actually have to do it in, it's like windows or time steps or some intervals. Okay, so in this way we reduce the high frequency noise in the component that was present over there. So this was the high frequency noise that we had over here, and then the output is smooth but it is distorted since the threshold will increase. So if I try and increase this threshold, it will vary. So those particular examples and the changes, how the pole will change or how changing the threshold the values will change, it has been shown in the video lecture. So you can again go and have a look over there. Again, the results are it's like very dependent and biased on the threshold value, but then till a point they are all undistorted, but then the high frequency noise will also occur over there. So it again depends on you that how do you want to sample your data, which particular threshold values are you it's like really wishing to see over there. Or it can be just that okay, you have given a feature to differentiate and then you just see it's like manually based on your own intuitions that okay, where a particular value would be there, so that I can it's like extract that feature from there. So you just input that value and take your data out. That's it. So I guess for this probably 5 tutorials were all based on that. Next, there's a tutorial that's Wiener filter. So that's something numerical and statistical based method. So we already have implemented, or we saw in maths that how Wiener filter was and how did we do the mathematics for the same. So we'll implement that Wiener filter on Tuesday. Apart from that, we'll go towards assignment and then it's like I got to know that for also there is very high likely chance that you will be given a MATLAB compiler, because the it's like questions they have set it up seems like you'll be getting something very similar, and on if not, then you actually have to know that if I have given a question, say write a ECG, it's like load a ECG signal and then filter it out using a transfer function like this, and I want to know what the filter responses would be, then you actually need to know that what sort of code you'll have it for there. So implementation holds also an important matter in signal processing actually. So knowing that will again help you, but it's like it's not that hard and fast, but just get to know. It's like if it's a pole zero plot, you know it's just PZ plot. If it's a frequency response, it's frequency Z. Then if it's a phase spectrum, it's like that. Others are more of based on intuition. So here you actually don't need to remember anything. Again, for cross correlation also you don't need to remember anything. It's just that taking a template, indexing it out, then you should know that okay, you know the formula. Now just add the formula in terms, it's like write the formula in terms of code. So that also, even if you see, you'll be able to get it. Or if not, then evaluate it. Okay, if you're not able to understand it, say if it's I equals to 1, then write I equals to 1, what the value would be, what the length of the vector would be, then you'll essentially get that what's the basic fundamental behind it. So you'll be able to derive it. So coding is no biggie, but it's just that you should know what the logic is following behind it, and you'll be able to do it. If there are any doubts, let me know, and else we'll go towards the assignment out of the previous week. That's it. Here. Any doubts? Or do you have any questions?
Ma'am, I have one question. Hello.
Hmm? Hello. I thought someone spoke. Okay, if not, then oh.
Ma'am, I have a question.
Yeah, yes.
I mean, some places, I'm like for calculating cross correlation and ma'am zero cross rate. Ma'am, there are pre-built functions in MATLAB. Ma'am, but sir is not using ma'am these pre-built functions. He ma'am manually, ma'am, he applies for loop if else condition. Ma'am, why is it so?
It's because, okay, so I'll give you same example as we did. So last semester I had a course called as digital image processing. So you know this Wiener filter, right? Then there are say frequent FFT. You might have done FFT. So but then our like instructor compiled us that, okay, constant us that you should not use any inbuilt function and you should develop it from scratch. We also felt a bit weird at first that why it's so and then why is not using it directly. It's just for your own understanding that you'll be able to, it's like, see through the process. It's just that there are different functions and libraries for this, and MATLAB is not that open source, but Python is. So in Python you actually can see the code behind the library function. In MATLAB you can't. So when you are doing something in MATLAB, it's always nice and better to know how the process is following through, is like from the scratch. If not, then you'll always as like do it and then you see, okay, this is a response, I got the response, this is a response, I got the response. Again, for transfer function also you have a inbuilt function where you essentially just write the coefficients. It will give you the transfer function, it will show you the transfer function, the frequency, magnet response, how it's varying, the trend, to show you all sort of things. So there's also different kinds of GUIs there in MATLAB, but it's just there to build up on your foundation and so that you can know how it works and from scratch to give you a basic understanding of it. That's it. If you know and you're well versed with it, for assignment use the inbuilt function, it's fine. But for exams I do guess so that you'll have, is like, you must know the entire process behind it, or perhaps won't be good for you then.
Ma'am, in this part of assignment in the week 10, we have almost every question on MATLAB only type of
Mm.
question. So you will tell today about how to solve these questions mathematically, or is there any mathematical approach today?
For week 10's assignment? No,
Yes,
right?
ma'am.
Oh, achha. You already solved it, right?
Yes, ma'am. It's gone.
Uh-huh. So I don't think so. It's more of very easy if you implement it in MATLAB. Else, it's like implementing a filter and then doing it. Then for that, you should again know that. What do you say?
No, no, ma'am. Like after fifth, after fourth question, huh? Fifth,
Uh,
sixth, seventh type
fine.
questions. Uh,
Yes. So I really don't think so. If there's, it's like, it's much easier because it's like you'll have to plot it on your hand. Then. That's why. So
and in
if
week 11 also, there are
hmm,
some.
week 11 is totally
If you,
MATLAB. I saw it. Oh,
if you
it
see so,
changed.
in some of
Is
the
it
questions, like in
24?
the RMS, like ZCR, they are given.
2024. How many turns? So if it says that, okay, just show it by MATLAB, it's fine, do it by MATLAB. But okay, this kind of question you can also implement it on your hand, right? Now you know how the function looks like, see how many zero crosses are there. But then the trick is that the time step is very smaller over here. So what you do is that do it for point one, you see it's like 2 times multiple of point one, and then you double the number of turns. So you get the value. Similarly, if it's for RMS, what you do essentially for is like for finding this root mean square error, or it is just root mean square value. Okay, so it's just the value of the signal. So you have to, it's like, take the square of all the values and then divide it up. So you can essentially compute this. You'll have a numerical calculator there with yourself. but then it's much more easier when you do via MATLAB. So I don't think so it would be asked via, it's like to do it on hands-on and no compiler available with you. I asked, they said that if there are questions associated with MATLAB, they'll give you a compiler. If not, then the questions would be somehow that you'll be able to solve. So something like this, it's something that you can solve it on your hand, so you have a basic understanding of it.
Okay.
Okay, so okay, we'll do the assignment then. Okay, so these are all questions with MATLAB. I just want you to know that how it's being computed. I have the code with me. I can show you the code. It's just that you should know that how it's being done. I hope the slide is visible. So it's like for a derivative based filter, we have a 0 over here, but no poles. What's the magnitude and phase spectra at the 250 hertz frequency? And number of points that are evaluated is nothing but 1000. So what we do is that here. So first, write the sampling frequency. Say our number of points in our entire signal is 1000. I hope it's visible here. And then give the numerator as our zeros. Denominator, we don't have any poles, so it's just 1 as a constant value. Then you normalize them up, write the transfer function for the same, take its frequency response, plot it, take the phase response, plot it, and then that's it. So now they told us to evaluate it at 250 hertz. So differentiate it and then see what the value can be approximately at 250 hertz. So here it's 0.78. Here it's approximately 0.7. So that's it. So 0.7 and then 0.7. Its answer is D. That's it. That was okay.
Yes, ma'am.
Cool. Next, and now here we have a pole. So we just add a new value towards the transfer function. That's it. So we add a newer coefficient over here. So we had this as our poles. Now you have one more way. Sorry, as our zeros, you have a pole over here. Normalize them, see the values, and then at 50 hertz they told us. So see the value at 50 hertz over here. That's it. At 50 hertz, at 50 hertz. Now one more thing over here can be asked is that okay, if your number of poles increases or number of zeros increases, what happens to your spectra? So those are kind of thing you should be even motivated enough that you is like just go and see, okay, now if it's negative 0.8, I did it negative 0.5, it varied like this. Initially it was like this. So you need to know how the response would vary, when it would be more steeper, when the slope increases, when it decreases, at how it's like at after which particular point of frequencies you see that your spectra is saturating or it's converging very nicely. So those are common points, are something that you should know, and you should be once like well versed with them. Okay, next question is like we have a signal that's generated. Now they have also given us a MATLAB code for the same. So they told us to filter it with a derivative based filter having a 0 at 1 and a pole at 0.99, and then to find the SNR using the same. So how do you find the SNR of it? So that's nothing but energy ratio. So question number 3, it's like, now I have timestamped a signal, reference signal is given. So let's see how and plot that, how the reference signal looks like. So we see, okay, it's nothing but a sinusoidal signal continuously varying. Okay, then you have a point, your noisy signal. So this is your noisy signal. So let's see and plot it. It's like this. So it's again sinusoidal, but then it's again in itself also it is sinusoidal. Okay. So then for finding the, it's like, now you can also do one thing is that try finding the SNR over here only. So you had your signal with a noise. Now you have a signal without noise. Sorry, you have a signal without noise, you have a signal with noise. Take a difference, find the ratio of energies. Then what they told us to do, it's like filter the signal. Now we have the pole zero specifications for the same. We made the signal, we filtered it out. Now we have to see how it does. It's like differentiates into. So it's like this. So it's been varied. Now what's the difference in between all three of them? Let's plot all of them together. Okay, so here you see, but then again you also see that there is some effect of noise which hasn't been eliminated from your entire signal. So initially your reference signal was this, which was then dumped by noise, so it became like this. Now when you filtered it out, it's like this. So you see that the specification of pole as 0 as 1 and then pole as 0.99 hasn't even sufficed your own condition, that you're not even able to eliminate the noise completely. It's like it has dampened it out somehow, but then here if you see your amplitude was 1, now your amplitude has been halved exactly, so it's 0.5. So you see that you have lost half as values of your data or amplitude of your data. Again, you have also sacrificed on your what you say, the frequency and the phase spectra of your data, so it's again essentially differentiating. So what you see, SNR would be just nothing but okayish value for it. So what we get SNR as 3.5. So normally, just one simple question, that what do you anticipate? The SNR should be higher or should be lesser? So signal to noise ratio, when you have a lesser noise in your
Higher.
signal, yeah, yes. So if you want your data to be filtered out nicely, and if it's more, it's like, you see, if it's ideally matching to your reference signal, how the SNR would be?
Noise energy should be tending to negligible. Like
Sorry.
SNR would be more. Noise energy should be negligible.
Yeah,
for
yes.
this.
So SNR would be higher.
Higher.
Yeah, yes. Okay. So that's how we find this how the size scenario. So here it came 3.49, answer is also A. Same is that what's the correct MATLAB command for generating the transfer function coefficients of Butterworth? So this I guess you might know. So we have a center frequency, then a sampling is given to us in the transfer function. So again, if it's a high pass, okay, the high pass filter is also given to us. So what the answer would be here?
The option.
D.
Yeah. So option is D, you just write it. So just remember this order, that first you have like this, don't divide the sampling first and then the center frequency first. You have seen many students to do like that. Just keep those things in point. Then, so find the numerator polynomial B and denominator polynomial A coefficients of the Butterworth high pass filter with this. So you have to implement it and see that how the values will be. Oh, I didn't write it. Okay, then it would be there itself. Okay, so it's like the same code function that you do over here, same, and then just see how the values would be for the same. Now here the order is equals to 2 is given in the question, it's also given. Then you have a Butterworth high pass filter, sorry, of order 2 and cutoff frequency is 100 hertz, and then you have to see that what's the magnitude and phase response at 75 hertz. So essentially the similar question that we did previously, there we only had pole 0 and then we derived and then saw how many it is. So similar thing we'll do over here, it was at 75 hertz. So we write it all, then we give the Butterworth filter, find its frequency response, plot it. Similarly, phase response plotted. So here it has been told to us at 75 hertz. What happened? So it's not exactly 75 over here, but can always scroll up. It's not a good technique ideally. What you can do is that go to the phase response vector and then at that particular index find the value of it. So you'll also get, or you can just write as phase of 75, so you'll also get that value over there. So this is like around 1.9. So you see in your option close to 1.9. Two options are close to 1.9, A and C. And then the magnitude. So it's like 0.4, 0.545. So this one. So C option. I didn't write answer for it. Yeah, the answer is C. Okay, you got it? You guys are proficient with MATLAB, right? So you, it's like this kind of code and bits you're able to understand them well, or do you need more help on this points? No, right? Ayush, are you trying to say something?
No, ma'am. Yes, ma'am. Actually, I am aware of MATLAB, ma'am. I have used it.
Yeah, that's nice. Good. So next question. So it's more of simple one. So we have given a transfer function. What's the difference equation for the same? So it's like essentially the step before forming a transfer function. So you can try it out. H of z is nothing but y of z by x of z, and then z raised to negative 1 is nothing but the delayed version. So what would be here?
B option or D.
Which one?
Ma'am, D option.
D option. Okay. Yeah, yes. So it's y of z minus x difference equation. It's like this. Okay. Next, which of the following statement is true for a derivative-based filter? So as the pole moves
A
close,
option.
which one?
A. A.
The distortion in output signal reduces. Not able to remove the wandering, we saw that, and the distortion doesn't increase. So the answer is A. Next, what is the output of convolution of a signal given in x variable with a filter whose numerator and denominator coefficients are given by this b and a that we have respectively? So what you have to do is that we have to essentially filter this particular value of x with the filter that's created from b and a. Okay, so how do we do that? It's like this. So you have your numerator coefficients, you have your denominator coefficient, you have your own vector, and then you filter it out. So with the respect to the coefficients and the signal that you have, so what you get is nothing but 1 and all zeros. So A option. Then at last, we have what's true for the Butterworth high pass filter. So the last, I guess, the second tutorial question. So what happens? The answer is there, but okay.
B.
E option.
Yeah, yes. So selection of an optimal order of filter as well as cutoff frequency is important to obtain a better response. So then it might be also asked that, okay, what is that optimal order, or at what happens at higher frequencies? So distortion increases, but then if it's not distorted, then the frequency, high frequency noise increases. So that sort of questions is like can be done here and there. So that's it for today. Thanks for joining. If you have any questions, let me know. Or next time we'll do this part. I saw. So from here we have tutorial 2 and 3 left. That is nothing but Wiener filter implementation, and then all of these on Tuesday. And then perhaps it's like previous assignment for week 11. It has been released yet, but I'll see if I have any access to that. So you're ready for the exam then? Only 2 weeks left for the course.
Ma'am, I have not done week 1 yet.
You have not done?
Week 1 yet. I have not revised week 1 yet.
Then do it. We'll have an extra session on say 11th or 18th. So I'm not so sure of the date. They'll let me know. So you can it's like beforehand you can tell NPTEL or the instructors that which particular topics you want to be revised on the live sessions. So I'll let you know. Or we can just do all the previous set assignments again. So that will also help in a way.
Ma'am, if we
Please,
do all the assignments seriously, then ma'am,
Huh?
will it be sufficient for the exam? If
Yeah,
we
it's
do all
more.
the assignments seriously.
It's sufficient, but then it's like, okay, what if something came up the point and you don't know? So it's nice if you go through all the lectures. I know if it's the time is cringe, then better go through the assignments at first and then go towards the lecture. If you have time, go towards the lecture then.
Ma'am, actually, there are plenty of formula and ma'am values. Like ma'am, when I was revising week one, ma'am, I saw a table of that EEG signal, delta, theta, normal, abnormal frequency,
Frequency
and ma'am,
responses.
yes, ma'am, and then a table of the amplitude of the QRS, R wave, P wave, then the duration of, ma'am, there is a lot much to ma'am mug up, and
Nice.
ma'am, infinite number of questions can be made.
Mhm. No,
What
so
is
it's like
the
this
Yes,
kind
ma'am.
of
Like, what is the action potential in depolarization, repolarization? Ma'am, a lot of values are there.
so see, for action potential it's always like it's -70 and it's +20, so those values are kind of standard. But if it's for EEG, say you have the 5 bands, so you should know ideally that has like what's the frequency ranges of those bands. So me being a biomed engineer, this thing is being repeated for me again and again, so it's kind of more up there. Then you have for ECG the amplitudes of the wave, so don't again mug up those amplitudes or how the duration of each one varies. Just see how the waveform is, then just from your intuition you should know that okay, the P wave is smaller than the T wave, the amplitude duration of P wave is higher than that of the wave, QRX complex is the highest one. If I have to characterize, I'll first find the RR interval, so something like that. So more it's like this mug up kind of questions won't come up, but something that's very standard and is following through ages might come.
Ma'am, like after each tutorial, after each question, ma'am, sir gives 2 to 3 observations
Yeah,
about the
yes,
assignment, like ma'am, we did in the 10th question. And ma'am,
yes.
there is no logic, ma'am. Ma'am, we have to perform the experiment, then only we can derive which
Yes.
of the following observation are true. So, ma'am, they are also very difficult to remember, ma'am. Therefore, I was asking that if we do all the assignment, will it be sufficient? Because, ma'am, we have to pass the semester, ma'am. It's important for credit transfer.
Yeah, true. It's like doing the assignment would help, but it's just that something if I asked from the concepts point of view, then if you're just your knowledge is just restricted to the questions from the assignment, would be somehow hectic for you. Then it's like if you go through the lectures, it's fine. You should know what the concepts are. You should follow along with the logic, not necessary to mug up everything. But yeah, following the logic is more of the thing. If you're not able to understand anything, and let the it's like post your comments in the Q&A here in the chat, or you can also let me know. So beforehand I'll also prepare some material for the same, can help you guys for the time.
And can you please ask Sudipta sir for the question paper?
If I can.
Like previous years also.
Previous years NPTEL doesn't give the questionnaires.
Yes, that's why. If you have any
I
link,
can try
something.
and ask. I'll try and ask if it's like if that's available, because this is also my first time paying for an NPTEL course. So I also don't know how rules go over here. I'll ask if that's available. I'll let you guys know. Okay, then I guess.
Thank you, ma'am.
Thanks for thanks.